Page 8 of Properties of Curves. Let's see, mark the number line, this number line, with a sign diagram showing when the function above, this function, is increasing and decreasing. Okay, so first of all, what I'm going to do is I'm going to use a highlighter and mark when this red curve is increasing with green. And actually, there's one more part that's increasing right there, right? Now, what about right at 3? Technically, it's not increasing there because the derivative there is just 0, right? Now let's mark the part of the red curve where it is decreasing with a red highlighter. Oops. This is the decreasing part. Okay, so now what we're going to do is we're going to transfer this information down to the sign diagram. So at the local maximum and the local minimum and the stationary inflection point, of course, the derivative is 0. And then in the green intervals, the derivative is positive, positive, positive. And the red interval, the derivative is negative. Okay, so there we've marked it when the function is increasing and decreasing, positive, negative. And then we can also mark it with zeros where the function is neither increasing nor decreasing. We did that too. We put zeros on top of those values. Okay. Now we're going to be looking at these sign diagrams here. In these sign diagrams, it doesn't specify the value of the critical points. In here, the way they mark their critical points is they put this vertical line, but I usually mark it with zeros because I think it's more clear. What kind of function has a sign diagram to the left? Okay, so if this is a derivative sign diagram, this is basically saying increasing, flat, increasing, right? And then this other sign diagram is saying decreasing, flat, decreasing. What kind of function has the sign diagram to the left? So basically it's increasing, flat, increasing. Does that sound familiar? Let's go back to page 7. Oh yeah, it's this function here. It's y equals x cubed. So y equals x cubed is a function that has that characteristic. Increasing, flat, increasing. All right. What additional check do we do if we are finding global maximum and minimum on a domain that it is a limited interval? So remember, if we have a limited interval like this function here, we do need to check the endpoints to make sure that these endpoints are not lower or higher than the local maximum minimums, which we find by finding the places where the ball would stop rolling away, stationary points, right? So we do need to check endpoint values, y values. Okay. Number 1, the tangents at points A, B, and C are horizontal. Yeah, so if I drew my tangent lines here, A, B, and C would have horizontal tangent lines. Classify the points A, B, and C. So this is very similar to the investigation, right? So this point A, I would call the local maximum, right? Local maximum. And point B is not a maximum nor a minimum. It's a stationary inflection point. And C is a local minimum. Okay, so we've classified A, B, and C. Draw a sign diagram for the gradient function f dash for all x values. Okay, so we're going to do something similar to what we did above. It's going to be a slightly different sign diagram. So to make the sign diagram, maybe it's helpful if I color in all the increasing portions green highlighter and all the decreasing portions red highlighter. And of course, there's going to be points that are zeros. And those 3 values are -2, 0, and 3 x values, right? And then the green portions are positive, and the red portions are negative. And there are no asymptotes, so I'm just going to erase these lines because they kind of look like asymptotes, and I don't want them to look like asymptotes. Okay, so I'm done with my sign diagram, which it asked me to do for B. State the intervals where y equals f of x is increasing and decreasing. Okay, so increasing, I'm going to write that in green. I would say below -2. I would say above x equals 3, increasing. And decreasing would happen from -2 all the way to 0, and from 0 all the way to 3. Remember, at 0 itself, it's not increasing or decreasing because it's just a stationary inflection point. Okay, so now we've finished part C. Draw a sign diagram for f of x for all x. Oh, so now it says to draw a sign diagram for function f, and we have drawn one for f dash, which we did for part B, right? So what is the difference between drawing a sign diagram for f and for f dash? Okay, so basically when you draw a sign diagram for the function f, you're kind of just drawing a function, or you're kind of drawing this graph in one dimension. And basically what you're saying is when the function is positive or above the x-axis, you're going to say the sign diagram is positive. Like, so from here to here, it's positive, right? And from here to here, it's positive. So these two parts are going to be positive on the f sign diagram. Okay, so it's a little bit different than on the f dash sign diagram. So where are the places where it is above the x-axis? From -4 to 0, and from 5 onwards. So I'm going to mark those important points. I'm going to mark 5, I'm going to mark 0, and I'm going to mark -4. And from -4 to 0, the function is positive. And from 5 up, it's also positive. And in between the other intervals, it's negative, right? So below -4, the function is negative. And below, between 0 and 5, the function is also negative. Do you see what we're saying with the sign diagram for f of x? Okay, so it doesn't have anything to do with the derivative in this case. It has to do with when the function is above water, when the function is below water. Number 2, for each of the following functions, find and classify any stationary points. Sketch the function showing all the important features. Okay, so let's do this first function, x squared minus 2. We're going to find and classify stationary points. Remember, stationary points are where the ball doesn't roll away when the derivative is 0. So let's take the derivative of this. We get f dash equals 2x. When is this derivative equal to 0? Well, we just solved the equation 2x equals 0. It's when x equals 0. So if we drew a sign diagram for this, it would be a pretty simple sign diagram. It would just have 0 in the middle. That's the 0. And then the derivative function is going to be positive on the right and negative on the left. Okay? So you know that the function has the shape going down, flat, and going up. And if we look at this, we can also remember that, oh yeah, this is a parabola, right? Okay, so we know that the function basically is going to look like, kind of like this, right? It's going to have its vertex at 0. Okay, now one thing that we know that we don't get from calculus, we can find the y-intercept, right? The y-intercept of this function, if we put in x equals 0, we know it's -2. So basically this parabola is going to go through -2. Okay, so why don't we draw it going through -2? And other than that, we know that it goes down here and it goes up here. Okay, so there is our function. Why don't we draw the function in blue? Okay, so that's A. What about C? C. So let's first find the derivative function. It's going to be 3x squared minus 3. And if we set that equal to 0, we can find the critical points, or when the function has minimums or maximums. So 3x squared minus 3 equals 0. I could factor. And from this factoring, I know that the critical points occur at 1 and -1. So if I drew a sign diagram, I would have a critical point at 1 and -1. Those would be the zeros. In between the two, if I plug 0 in here, I would get negative times positive. It would be negative. If I put in a big positive number, I would have 2 positive. If I put a big negative number, I would have two negatives times each other, so that would be positive 2. So basically, the function is going to increase, flat, decrease, flat, increase. Okay, and when do the increase or the flats happen? At -1 and 1. So we could draw a sketch of this function saying that, okay, at -1 and 1, the function is momentarily flat. And in between, the function goes up and down and up again. Okay, now we could find out one additional important piece of information. If we find the y-intercept, we can find the y-intercept easily by plugging in x equals 0. So the y-intercept is 2, right? And oh, I just happened to draw it right at 2. Let's see what else they ask us to find. They do say find and classify any stationary points. We did find that one of the stationary points is x equals -1. The other stationary point is x equals +1. We can also find the y-coordinates of these stationary points, right? If we just plug in -1 and 1 into this function, we can find the y-coordinates. So if we put -1 into here, -1 cubed is -1. -1 times -3 is +3. So 3 minus 1 is 2. 2 plus 2 is 4. So it would be -1, 4 is one of the stationary points. The other stationary point we can find by plugging in 1. So it would be 1 cubed, which is 1, minus 3 times 1, which is -3. That would be -2 plus 2 is 0. So the second stationary point would be 1, 0. So now we can do a better job of graphing our function, because now we know exactly where the two stationary points are. One of them is at 1, 0. And the other one is at -1, 4. And now we can draw a much more accurate graph. Okay? And if we wanted to classify the stationary points, of course, this will be a local maximum, and this will be a local minimum, and this will be a local minimum.